Hello, my name is Fahim and today we're going to talk about work and energy. Now, work and energy methods are used to solve problems that are too difficult to solve using the force equations. Now let's look at what is work. A work done by a body as it moves from position 1 to position 2 is defined as a product of the force and the distance the body covers or moves in the direction of the force. So the equation of the work is force times the distance covered from position 1 to position 2, that's S2 minus S1. And the units of work is Newton meter. So let's look at an example. When a body moves from position 1 to position 2, and the force is applied in the direction of the motion, the work done is equal to force times the distance between position 1 to position 2, that's S. And now, if the force is applied at an angle to the direction of the motion of the object, we have to consider the angle, which here is alpha. So the work done is force times cos alpha to find the component of the force acting in the direction of the motion times the distance covered. But if the force is acting opposite to the direction of the motion, so we have to take the component acting in the direction of the motion, so we have to take it as negative F cos theta times the distance covered. So in easier terms, work done is the product of the distance moved and the component of the force in the direction of the motion. Now let's look at what's energy. A system possesses energy if it has the ability to do work. Work shifts energy from one system to another, and energy is a scalar quantity. Now energy can exist in different forms. There's kinetic energy, there's potential energy, and there's elastic energy. Kinetic energy is the work done on a particle by bringing it from a state of rest to velocity v. The equation is half mv squared, whereas v is the velocity and m is the mass of the object. Potential energy is the energy possessed by a body by virtue of its position relative to others. The equation is m, which is the mass, times g, which is the gravity, and h, which is the distance between the two positions. Elastic energy is the energy absorbed in a spring when stretched or compressed from its unstretched length. The equation is half kx squared, where k is the elastic constant and x is the distance between the stretched or compressed length to the unstretched length. Now let's look at the work-energy relationship. A change in the total energy of the system is brought about by either doing work on the system or by adding heat to the system. Now for dynamics problem, we only consider kinetic, potential, and elastic energy. The change in energy of a system between two states is referred to as U from position 1 to position 2, or state 1 to state 2 is equal to U2 minus U1. So the work done in a system is equals to the change in internal energy of a system. So we can say that U12 is equal to W12. From here, we can get the work energy equation, which is U12 or W12 is equal to del T, which is kinetic energy, plus del Vg, which is the potential energy, plus del Ve, which is the elastic energy. The equations are mentioned here, and we have to look at force. Force is an actual and external force. F is an external force because of that it's mentioned in work, whereas M, G, N or R are internal forces, so it is relative to the energy that the body the energy that affects the internal energy of the body. Now let's look at an example. A slider was released from position 1, and as it slides from position A to position B, we have to find the maximum velocity of the slider as it reaches the bottom at B and the maximum deformation of the spring. Now, in order to find the velocity at B, we have to first of all take the equation, the work energy equation. Now, as it slides down, there's no external forces applied to this slider, So the work done is 0, and the spring at B is not yet deformed, so del V is equal to 0. So the work energy equation comes down to del T plus del Vg is equal to 0. So since VA is at rest, so VA is 0, so the equation of the kinetic energy is simply half times m times Vb squared. And now the Vj, which is the potential energy, is mgh2 minus h1. So since it's moving in a circular position, so we can say that the distance from here to here is simply the radius of the curvature, which is 0.6. And as it moves from an upper position to a lower position, it's a negative force here. We consider it as negative. So it's simply half mvb squared minus mg times 0.6. So we get the velocity of the slider at position B. Now to find the maximum compression X of spring from position A to position C, which is the maximum deformation of the spring. So let's just say that C is somewhere here. Alright. So now we have the work done from A to B is again 0, and del T, which is the kinetic energy, is also 0. So the equation comes down to del Vg, which is the potential energy, plus del Ve, which is the elastic energy. We have the potential energy from the previous workings, and now we have the elastic potential energy, which is half times k times x2 square minus x1 square. So it's just the distance from B to C. Alright, so half times k times x square minus mg 0.6. We solve it and we take the value of k as given to us, and we get the value of x as 48.5. Now the value of k is always given in a problem, or in other problems we have to find the value of k given the other results, like for example the final position or the initial position. So thank you, I hope it helped you. Alright.